Hello class, welcome to the next lecture on signals and systems, and in this lecture we will be talking about a specific class of systems called as LTI systems and an operation known as convolution. Okay, so in the last lecture we had gone through the different classification of systems, right? We had linearity, time invariance, causality, stability, things like that. So out of that I had mentioned that two of them were sort of important, which were linearity and time invariance. Right. And what we do is we combine these two properties and we call certain systems which satisfy both of these, that is systems which are both linear and time invariant. Okay, and we call them LTI systems. What is it from? Linear time invariant systems. So it basically follows linearity and it follows time invariance. So what is the importance of this? Why is this linear time invariant concept or this property? Why is it important? Because it helps us model the system using mathematical function, right? Suppose we have a system, okay, we have system H, right? When given an input x of t, it gives an output y of t, okay. And suppose when I give an input delta of t, okay, what is delta of t? Delta of t is an impulse function, okay, to the system, I get an output, right? So we can call this as the impulse response, right? We can call this as the impulse response of the system. So why is impulse response important? So I hope you guys remember the shifting property of an impulse, right? What is the shifting property of an impulse? Shifting property of an impulse was integral minus infinity to infinity x of t delta of t minus t naught b of t is equal to what? X of t naught, right? Basically what is happening, what we can do is if we have an impulse, we can we can find the values of any signal at each point of time. All we have to do is what? We have to find the integral for t. We just have to change the value of t0, right? From t0 equal to 0, 1 to whatever, or 0, 0 0.1, 0 0.2, etc., 1, 1.1, etc., so on and so forth. If we do that, what we get? We'll get x of 0, x of 0.1, like that. So basically we can get the values of any function at any point of time if we can do this, if we can use this shifting property of impulses to that, okay, right? So keep this in mind, okay, let this be in your mind for the time being. So one thing is the shifting property, and let me call this impulse response as h of t, okay. And what is, other than this, what is the significance of impulse response? I think I have mentioned this when we were dealing with network systems, electrical networks. What was that? That this shows the natural response of the system, right? Natural response of the system. That is basically we are just giving a spike. We are just exciting the system. We are just exciting the system and we are seeing, okay, if we just excite it, how will it respond. So we are just, we will get a what fairly good idea regarding what a system is. So this is okay, let's keep this aside for a moment. The most important part is, if we have an impulse, we can do this. Okay, and suppose I have a system with impulse response h of t, right, and I'm giving the inputs different inputs, right, and what will be these different inputs? They will be different impulses, and they will be weighted and shifted in different ways. Okay, what will I get? I'll get what certain responses, certain impulse responses, right? Something like I'll get a0 h of t minus t0, a0 h of t minus t1, like that. Basically what is happening, I'm if I give a simple impulse, I can get a simple impulse response. If I give a scaled impulse, scaled and shifted impulse, what do I get? I get a scaled and shifted impulse response. Okay, how is this possible? This is possible because of the LTI nature of the system, right? And now what happens if I add all this and give it together? And suppose how I get this? Suppose that I get these values from our x signal, right, from our signal x of t. Okay, that is, if I have a signal like this, instead of giving this signal as a whole as to an impulse to the input of the system, if I find an impulse whose weight is this much and I give it to the input, I get a certain output. Then I find an impulse and shift it this much and give the weight of the impulse as this much and give it to the impulse, so as to the system, and I take the output. Then I do this for each and every moment. I may be drawing like this, but consider for very small increments, and I get all these outputs, and if I sum it up, what am I getting? Basically I am getting the response of the system to this input, right? So what am I doing? I am finding the response of the system to each and every point of the input signal. And how am I finding that? I am finding that by applying an impulse which is weighted and shifted corresponding to the value of x of t at that point and that point in time, right, depending on what t is, t0, t1, etc., like that. That is, I am getting an output at the system for each impulse which is corresponding to each point of the input. Then what am I doing? I am adding them up. Okay, so this concept of dividing the input into smaller, very much smaller intervals of time, then applying the weighted impulse to the system, then finally adding the whole thing up. This concept is called as the convolution. Okay, and when it comes to a continuous time system, it becomes a convolution integral. Instead of a summation, it becomes an integral. Okay, so I want to define this convolution integral. Okay, so This much I was telling so that you will get an idea regarding what a convolution integral, instead of directly jumping into the mathematical definition. Now I hope you understand what the logic behind this is. Okay, now what we will do, we will see the proper definition. Suppose we can the first step that I mentioned, that we are dividing the whole thing, right, whole signal into impulses. That is what we are doing is minus integral into infinity x of tau delta of t minus tau d tau. Here t is the shift. Okay, t is not the variable of integral, tau is the variable of integral. I am just changing it. So basically what am I getting? I am representing my input signal as what? As a weighted, as a sum of, or an integral of weighted and shifted delta functions, impulse functions. Okay. Now using this definition I am going to write what is y of t. Y of t is h of x of t, right, that we have already defined established from the definition of a system. Okay, now I am giving it, so this is integral minus infinity to infinity x of tau delta of t minus tau d tau. Okay, now again, now since this is a linear system, I can change the order of operation. So I am bringing this out. Okay, and I am applying this h to the delta function, minus infinity to infinity x of tau h of delta of t minus tau d tau. Now what is this? What is this term? Basically we had defined, if we give delta of t, we get the impulse response h of t. So if we give delta of t minus tau, what do we get? We give h of t minus tau. Simple. So this is again, what is this? This is equal to integral minus infinity to infinity x of tau h of t minus tau d tau. This is the definition of this is the mathematical expression for a convolution integral, that is y of t is equal to minus infinity to infinity x of tau h of t minus tau tau. Okay, here the variable of integral is tau, and t is a shift, like obviously you can see it is a folded, that is flipped and shifted version of the impulse response. We will come to that, we will see problems, so we will have a better understanding. Okay, and t is the shift and tau is the basic time value or the time variable in this expression, and t is the shift that we are using. So basically you should understand that in the language of convolution, the output is a function of the shift that we are giving. Okay, and this is represented as x convolution h. Okay, this operation, this whole operation is denoted using star. So I will just go through it once more. So what we are doing is we are taking the first of all we have the shifting property, like that is if we multiply and integral any signal with delta function, impulse function, shifted delta function, then we will get the values of that signal at that particular point. Okay, that is the first concept. Then the second concept is that we have a system x of t gives y of t. To that system, if we give an impulse delta of t, the response of that we call as the impulse response, and we use the term h of t, and that h of t is used to characterize each and every delta LTI system. And why is that? Because an impulse function sort of gives the very most natural response of a system, because it just momentarily excites the system and then nothing else is there. There is no other signal to give a forced response. So an impulse response gives the most natural response of any system. Okay, so that is one thing. That is why we are using a delta function, and because of the shifting property. Shifting property is very important. Shifting. Okay, so we have established a shifting property. Then what do we do? Now we take a signal and we break it down into different impulse functions using the shifting property. Okay, so basically we have an impulse for each and every moment of time for our signal. And then what do? We pass every each of these impulses through the system, and we get the corresponding response, and we add it up to get the response which we would have got if we had directly given the x of t as the input. And why are we doing this? So that we can assess the system mathematically. So that this process of representing the output as the weighed and then a sum of weighed impulse responses is called the convolution integral in terms of continuous signals, and convolution sum in the case of discrete functions or discrete systems. Okay, so mathematically let's have a look at it, how we do it. First we represent the signal as a sum or integral of the different the different weighted impulse values, impulse functions. Okay, here we are using this t, and we are keeping on shifting it so that we get the whole signal. Okay, then what do? We represent the output as the h of that particular input. Okay, h of x of t. Then we represent x of t using the above said formula or above said expression, and then we change the order of the operations, right? And why are we not taking h of x of tau here? Because h of function works on variables with the or functions with the t variable only. Here only delta has a t variable, h doesn't have a t variable, it only has a variable tau. So therefore this function can, for this particular function, delta x of t, x of tau seems like a constant value, so it doesn't matter, so directly goes to delta of c. So what do? We write minus infinity to infinity x of tau, h of delta of t minus tau, and we know that h of delta of t is h of t. Similarly, by linearity principle, sorry, not linearity, time invariance, my mistake. By time invariance, delta of t minus tau should give h of t minus tau. Therefore, we have minus infinity to infinity x of tau, h of t minus tau d tau. That is why, because for this part linearity is required, and for this part time invariance is required. That is why we are choosing linear time invariant systems, because only if the system has these two properties we can model and analyze these kind of systems. And finally we just write it down as y of t. We represent y of t is equal to x of t convolution h of t. And convolution is represented using star. It is a mathematical operation. And what is the expression for that? It is minus infinity to infinity x of tau, h of t minus tau d tau. Okay. Now let's see the convolution sum. when it comes to convolution sum, it is the same concept, just that instead of integration we have what, a summation. Actually, in fact, it may be a little bit easier to understand. Suppose we have a signal like this. Okay, what do? We split this thing, right? We split this thing into different impulses, right? Sorry, this is not a different shifted weighted impulses, right? And then instead of giving this to a system and getting some sort of output, what we do, we give these separately. At least theoretically, this is how we analyze it, right? So basically, if we add these all up, we will get this one, and we get what, a separate response for each of these, right? And since all of these are impulses and they are weighted shifted impulses, right? And the definition for, if we give a unit impulse, we get the h of n, impulse response, right? So here we have some, say, a0 h of n minus 0, a0 a1 h of n minus 1, a1 so let's call this a1, a2 h of n minus 2, so on and so forth. And finally, if we add this all up, we will get this, the response. This is how we analyze. In the continuous time version, what we did, instead of splitting this for t equal to 0, 1, 2, etc., we split it up into infinite different things, and instead of using the unit impulse, discrete impulse, we use the continuous time Dirac delta function. Okay, and we added it up to find the, or we integrated it to get the original signal. Similarly, here we are adding it up to get the original signal, and the response we are getting at as weighed and shifted impulse responses, and we are adding it up to get the output, and earlier we integrated it to get the output. Only that is the difference, right? This is the basic concept. So now let's convolution sum. Let's write it down formally. X of n is equal to k equal to minus infinity to infinity x of k delta n minus k. Okay, and y of n is equal to h of x of n. This is pretty much the same thing as what we did earlier. K is equal to minus infinity to infinity x of k delta of n minus k. Okay, now rearranging the order of summation, what do we have? We have summation k equal to minus infinity to infinity x of k h of delta n minus k is again equal to summation k equal to minus infinity to infinity x of k h of n minus k. So we can represent this as y of n is equal to summation k equal to minus infinity to infinity x of k h of n minus k, which is equal to x of n convolution h of n. This is the expression for discrete convolution, discrete time convolution. Okay, so basically let me just write down what we have been trying to say all this along. The output of the system is expressed as a sum or integral depending on the case of weighted and shifted impulse responses. Okay, this is the essence of convolution, and because of this weighting and shifting and finally summing it or integrating it, we need we can do this analysis only to LTI systems. That is why, that is the significance of LTI. Why? Because LTI systems allow us to do convolution. Okay, only if LTI property is satisfied, we can do convolution. So that is what convolution is. So this is the theoretical part regarding convolution. So I am going to stop this lecture here, and what I will do is in the next lecture I will give a step-by-step procedure of how to do convolution, and we will solve a problem. Thank you.